Hello, thanks for joining me today on the Leukopak Lady. In the last episode, I asked whether a donor can be over-optimized. And while donor optimization improves performance, over-optimization can make your process fragile and expose it to the same variability issues as not optimizing donor characteristics at all. So this leaves the real question: how do we design systems that tolerate reasonable biological variability from the beginning? The answer is not more optimization, it's engineering. So donor biology is inherently variable. This is a constraint, not a failure. So the goal is not to eliminate variability completely or find the one perfect donor. The goal is to design a system that performs reliably within expected variability. Engineering consistency means defining the boundaries your system must operate within. This includes defining acceptable ranges for donor biology, understanding how those ranges impact manufacturing performance, and designing processes that perform consistently across those ranges. This is not the best case scenario, you're designing for the expected case. So let's connect this process design back to donor strategy as discussed in the last episode and others in the season. Donor qualification defines your input. Donor stratification eliminates obvious sources of variability, and master donor banks help you manage it all. But this is only the beginning. That biological understanding must be built into process design. This looks like input specifications that actually reflect biological performance, process parameters that are tuned to expected variability, and predictive metrics that link specific aspects of donor biology to manufacturing outcomes. This is where biology becomes engineering. You must design your processes for robustness, not peak performance. A high-performing donor does not guarantee a scalable process. A robust process performs consistently across many donors. So instead of asking, who is our best donor, ask, what range of donors can this process reliably support? This is a fundamentally different mindset. And remember, engineering systems require feedback loops. Manufacturing outcomes must inform donor selection. Donor data must inform process adjustments. Both donor specifications and performance must be tracked over time. Without feedback, variability remains unpredictable, but with feedback, variability becomes manageable. So you're now shifting from science to systems. Early development is science-driven, but scale requires systems thinking, which means less reliance on individual expertise, more reliance on defined processes, less adaptation, more control. Consistency at scale is not achieved by reacting, it's achieved by designing. Keep this in mind though, you can design the best donor strategy and the best manufacturing processes, but if the infrastructure around it isn't built to support that system, consistency will still break down. So the next question should be, is the industry built to support this level of control? Are collection centers equipped to operate this way? Are cryopreservation strategies solving the right problems? Do we have the right talent to execute these systems? Because the next bottleneck in cell therapy is not just biology or manufacturing, it's infrastructure. So join me for the next 4 episodes as I explore how collection centers, supply chains, and industry structure must evolve to support scalable cell therapy manufacturing. See you then.